Today's topic is kind of complicated. It's kind of mathematically a little awkward, but we're going to go through it, and we're going to see that a mass spring system oscillates in the same way that a particle goes in uniform circular motion. It's very mathematically similar to the rotational motion that we studied in the last unit, and is very similar to what we're doing here with simple harmonic motion. So let's imagine here we have a nice flat smooth surface. There's not going to be any friction or air resistance or anything. This is going to be 0, and here we'll have some kind of spring attached to this, and we're going to pull it back this far. So we're going to pull it back for this far. This is going to be my maximum displacement, and I'm going to call that maximum displacement my A, and A equals amplitude. The amplitude is the maximum displacement from the equilibrium position. So the spring right here applies no force, but I pull this back, and then I release it, and then it's going to oscillate back and forth forever. If there's no friction, it'll oscillate forever. Now there is friction in real life, but we're going to ignore it. Okay, so that'll go all the way out here to negative A, and it's going to oscillate like that forever. And this has a mass of m, and this has a spring constant of k. Now, I'm going to derive an expression for the velocity of this mass as it bounces back and forth in terms of the amplitude and in terms of its position x. Let x represent its position along the x-axis where the origin is the equilibrium position of the spring. Now, it's only going to go between negative A and A. It's not going to come out here, for example. It's going to oscillate back and forth in here. So I want to know, okay, how does the velocity vary with that? Well, first of all, we're going to use energy. E, energy. Not just any energy, mechanical energy. Mechanical energy is kinetic energy plus potential energy. What kind of potential energy do we have here? Elastic potential energy, right? The potential energy of a spring. So this is going to be equal to, well, this is just going to be 1/2 mv squared. And this is going to be 1/2, what's the potential energy function? 1/2 kx squared. Okay, so I'm going to use this idea to get it. Now, also, the total amount of mechanical energy is equal to, well, when you're at your maximum position, your amplitude, what is your kinetic energy when you're all the way out here? Well, the object is turning around. It's stopped, right? At the very end. So its kinetic energy is 0. So all of its energy is like, when it's right here at the edge, its kinetic energy is 0, so all the energy is 1/2 ka squared. When x equals a, there's no more velocity. Velocity is 0, and all the energy is in the spring. Now, what happens when you're at the very center? Well, when you're at this position right here, there is no elastic potential energy. All the energy is in the motion of this object, and so that's going to be equal to 1/2 mv squared. But what's true about the velocity at the very center? It's at its maximum velocity squared. So 1/2 ka squared gives us 1/2 mv squared. Now we can use this. I can solve this for the maximum velocity. I'm going to do that real quick. I'm going to say, hey, 1/2 ka squared has to equal 1/2 mv squared. Well, the 1/2 goes away. If I solve for v, the maximum velocity, that's going to be equal to k over m, right? Divide by mass, and then we have a squared. The 1/2s went away, and then I have to take the square root. And that just makes the square go away. So look, the velocity, the maximum possible velocity, is going to be equal to our amplitude times the square root of the spring constant over the mass. Now this is a big deal. We're going to talk about this later. Okay, now we're gonna take a look at this expression, and we're going to solve it in terms of, see, 1/2 mv squared plus 1/2 kx squared equals, now I'm going to leave it in terms of 1/2 k a squared. Okay, the kinetic energy plus the potential energy equals the total energy in the system, which is also the elastic potential energy at the amplitude. Now I'm going to solve this for V. I'm going to get an expression for V. First of all, the 1/2s go away, and I'm going to go mv squared equals ka squared minus kx squared. Then I'm going to divide both sides by m. V squared equals k over m times a squared minus k over m times x squared. Now this is, I could stop here. I'm not going to, though. I'm going to do something to this thing. And remember, this is a proof. You don't have to know how or why I did this. Well, the how you should know. I can multiply this term by anything as long as it's equal to 1. Do you see that I can multiply this by a squared divided by a squared? Did you have a question? Okay. Now, right, this is legal. Do you see that this is legal? Because it's a squared over a squared. It's just like, I didn't change it. But it does let me do this little trick. I'm going to go v squared equals, I'm going to factor out a km and a squared, km and a squared from both terms. Km a squared equals, not equals, times. Well, what's left in here in these two terms? Well, km a squared, I took all of it, so there's only one, minus, and then what's left over here? An x squared over a squared. Now, I'm going to solve for v now. So v equals, take the square root of both sides, but it's plus or minus the square root of k over m times a times 1 minus x squared over a squared. Oh, and look at this. I got a square root of k over m times a. Well, that's my maximum velocity. So my velocity is equal to plus or minus my maximum velocity times 1 minus x squared over a squared. Oh, what did I forget to do? Take the square root of that. Okay. Now, this is our end result for right now on this side. So, but it's kind of useful. If you know where x is, and you know what a is, and you know what the maximum velocity is, or if you know the spring constant in mass and amplitude, you can figure out how fast you're going anywhere in this, along this path as it oscillates back and forth. And remember, the plus or minus just means, is it going to the left or is it going to the right? It can go to the left or the right. Like if x is equal to like 0.5 meters, like right in here or something, put in the 0.5 meters, and well, the velocity could be going that way or it could be going this way. Same is true on the negative x side. It can be going either direction, but this will be its speed, really. If you take away don't worry about the positive and negative. All right. Forget all this for a minute. Forget all this. Now we're going to look at a different situation. Like I showed you, that wheel. Suppose I have a wheel. Trying to make a nice circle here. That's pretty good. Not bad. Better than the other ones I did. Now, and I'm going to, here's my x-axis. Here's my y-axis. Okay. Now here's my dot. You know that dot that I put on the wheel? I'm going to put that dot right there. And then I'm going to put this wheel in motion. Now you have to use your imagination here. You have to think with cartoons. Let's imagine this wheel is just going around and around and around at constant velocity, or constant speed, constant angular velocity. Does that make sense? Assume constant angular velocity. Omega in radians per second. It's going around like that. Well, if that's true, then we've got a velocity that is tangential to this. Let's try to draw this. You know what? Hold on a second. Sorry. I don't do it like this. Oh, I drew it too close to the top. That's okay. Okay. So this is my maximum velocity. Okay. Actually, the velocity is constant, but I'm going to call it Vmax because I can call it whatever I want. But what I'm saying is that this velocity as it goes around this circle is a constant. Now this, normally we call this the what of the circle? The radius, but I'm going to call it A. Now I can do that. I can call it whatever I want. It's just the radius of the circle. We're going to call it A. Okay. Now, what we're going to do is we're going to watch this circular motion, but we're going to, this might be a good way of doing it. We're going to watch this circular motion. Oh, the dot got erased. Let's put the little dot right here on my little top. And it's spinning with constant angular velocity. Okay, and this is its velocity vector, and it's just going to stay constant as it goes around this circle. And it's going to have a radius of A. Now, first of all, this is going to have a position X. That's where this dot is on the x-axis. But watch what I'm going to do. I'm going to imagine if you're looking at this. I wonder if I can do this. I just thought of this. I'm going to try this. And I'm going to make a little flag out of this. Okay, see that little yellow post-it note flag? And it's rotating in a circle like this. But what if I look at this edge on? Let me get an edge onto the camera. Yeah, it's not working very well because I can't. If I look at it, if I tilt it like this, what if I just look at the horizontal, the x component of the motion? So in other words, if I took this and I looked at it edge on, so like here's the table, and maybe I'm looking at it edge on, and so here's as far out as it'll go, A. Here's the very center. Here's the edge. Here, this is at negative A. And this is our x-axis. And here's where the object is, right here on X. Now, as this thing spins, what if I look at just where it is on the x-axis? What's this thing going to do? Well, it's going to start here, and as it spins like this, it's going to go like this. You see it's just going to oscillate around, back and forth like this. This little dot, as this thing spins around, is going to go back and forth like this. There's a lot of animations you can find online where it does this. Okay, well, I'm going to call this angle theta from here to here. Now, I'm going to do a little bit of geometry. I've got a triangle here. I've got X. I've got A. Now, what would this distance here be? If I'm looking at this right triangle. Here's this. Its X component, its Y component, and here's its position right here. This is X. This is A. What would this leg be? Well, it's a right triangle. So I would use Pythagorean theorem, right? So this is going to be the square root of the hypotenuse squared minus x squared. Ooh, that kind of looks familiar from what we did before, doesn't it? Actually, let me zoom in. Sorry, I'm going. If you want me to zoom it in the back, you can just say zoom in. All right. And then if I am off screen, you got to tell me. All right. So now what I'm going to do is this. I'm going to make I'm going to do this. I'm going to make a parallel line to the x-axis, and if this is theta, then this is theta. Does everybody agree with that? Alternate interior angles. Okay, now watch. Now I'm going to take this maximum velocity and I'm going to break it up into its x component. That's my velocity in the x, Vx. And this is Vy. Okay. Now, if this is theta here, then this is theta here. But A and V make a 90-degree angle. So this angle right here is 90 degrees minus theta. Well, if this angle here is 90 degrees minus theta, what does this have to be? It has to be theta because this is 90 degrees. This is 90 degrees minus theta. Well, then there has to be 180 degrees in a triangle. So I just showed that this angle up here has to be theta. Well, that means I've got a triangle here, velocity in the x, velocity in the y, and velocity, the maximum velocity, is a triangle. So is x, and then root x squared minus x squared, and then a here they're similar triangles because they have the same angles in them. So now I'm going to do another little trick, which we often do with similar triangles. I'm going to set up a ratio. And I'm going to say Vx, see how this is opposite to this angle? Vx, look at Vx, right here. This is Vx. Vx is to Vmax as what is to what on this triangle? Well, Vx is opposite. It's opposite from the angle. So this is good. So the opposite of this angle is square root of a squared minus x squared over the hypotenuse, which is a. Okay, now does everybody see what I did? Sorry, it's a proof, so you have to go through all these little details. Again, I'm not going to require you memorize this proof. I just want you to see it so that you know I'm not pulling these equations out of, somewhere unspeakable. All right. Now, I'm going to solve this for Vx. So the velocity in the x is equal to Vmax times the square root of a squared minus x squared over a. But now watch what I'm going to do. I'm going to do the same trick I did before. I'm going to take this x squared and I'm going to multiply by an a squared divided by a squared. Then something almost magical happens. Vx. Thank you. So the velocity in the x direction here is equal to our maximum velocity. Well, I can factor out an a squared now. This is a square root of a squared 1 minus x squared over a squared. And this is all over a. Well, what is the square root of a squared? It's a. So this cancels this. And I'm left with Vx equals Vmax times the square root of 1 minus x squared over a squared. Okay, folks, prepare for a little mathematical chill to go down your spine. Well, maybe that doesn't happen to you, but it happens to me. That's why I like physics. These are the same mathematically. These are the same. They obey the same mathematical structure. This I developed from conservation of energy. And I got this equation. This I got from little geometry things, but they're the same thing. And what it means is that the mathematics of rotating motion up here can be used to describe simple harmonic motion over here. This is awesome stuff. And I got really excited because, I've been teaching AP Physics C for 25 years. And when we got to this section and I read the book and I thought, I wonder how they're going to explain this stuff without using calculus. Because we use calculus to derive this stuff in AP Physics C. And I read this and I went, wow, this is cool. I've been a physics teacher since 1993 and I learned something new, which is kind of fun. I'd never seen it done this way before. Very cool. Now, let's talk about that maximum velocity. Okay. The maximum velocity, well, that's just the velocity of it going around a circle, right? Now, what do we know about that maximum velocity? Am I still on screen? No, I'm not on screen. All right. Let me zoom out. I'll try to write big. I want all this to fit. See, the maximum velocity for this, well, it's really speed. It's the distance around divided by the period. That's what we want. We want the period. So this is going to be 2 pi, but what are we using instead of r? 2 pi a. That's the distance around this circle one time. We're going to divide that by the period. Well, I'm going to rewrite this. The maximum velocity is equal to 1 over the period times 2 pi a. Well, what is 1 over the period equal to? It's equal to our frequency in hertz, frequencies in cycles per second. Now, we said before that frequency is equal to our angular frequency in radians per second divided by 2 pi radians per cycle, because we want to end up with cycles per second instead of radians per second. So if this is angular velocity in radians per second, we divide it by 2 pi radians per cycle, and that ends up with cycles per second. So this is the conversion between frequency and angular velocity. Well, this is the angular velocity of this thing spinning around. Well, now I'm going to substitute that in. Our maximum velocity is equal, yeah, it's pretty windy and raining, pretty hard out there. Good, we need it. It's the frequency times 2 pi a. Okay, don't let the weather distract you because we're almost done here. Well, what goes away? 2 pi. So, my maximum velocity is equal to the angular velocity times the amplitude. Now, this makes total sense. This is what we did in the last unit. That is, my linear speed going around this circle is just equal to my angular velocity times the radius, the amplitude. All right, we're not going to die. Okay, so, well, we might, but at least we'll be doing physics. Hold on, this is the killing part. I'm so mad. But look, maximum velocity over here with this mathematics, the maximum velocity was equal to the square root of k over m times a. What does this mean? This means that the angular velocity of this mass spring system is equal to the square root of k over m. If you have a mass spring system, if you know the spring constant and you know the mass, you can figure out how many radians it will go through per second. Okay, now, I'm going to quickly go through this. So what about the period? Well, the period is 2 pi divided by the angular frequency. That's another equation that we developed earlier. Right? This is 2 pi radians, and this is radians per second, so you get number of seconds in 2 pi radians. That's the period. Well, what is 1 over the frequency? Well, this is going to be equal 2 pi times the square root, well, it's the reciprocal of this, m over k. So, the period of a mass spring system equals 2 pi times the square root of the mass over the spring constant. Voila. This is cool stuff. We can now make predictions about it. Also, look at this. If we look at where x is here, I can develop an equation to describe what x is. Well, we know what x is. X is equal to a cosine theta. But if this is moving around, let's say it starts here, and it moves in a circle around like this. At t equals 0, it's right here, but it's moving around like this. Well, we can say that theta is equal to the angular velocity times time. A in radians, or theta in radians. So x equals a cosine omega t. But we know what omega is. It's the square root of k over m for a mass spring system. So I can now describe the position of this mass spring oscillator as being a cosine omega t, but omega is the square root of k over m times t, times time. And I can now describe the simple harmonic oscillator as a function of time. That's really cool. Now, last thing, well, there are other things too, but I seem to be getting to the same part of this lecture, and I don't want to lecture on it too long. You are going to have to read the book. I do want to briefly talk about simple pendulums, though. So let's talk about a simple pendulum. A simple pendulum is this. Am I on screen?
Yeah.
Simple pendulum. And this, well, I'll get this done. You'll get out of here on time. Well, actually, we'll derive this next time, I guess. But this is theta. The restoring force of this is a component of gravity that's equal to mg sine theta. But if theta and sine theta are very small, if you keep the angle fairly small, sine theta and theta are the same thing if you express theta in radians. Now what this does, you go through the same mathematical ideas that we just went through, and we'll do it again later, but you end up with the period of a pendulum equal 2 pi times the square root of the length of the string divided by the acceleration of gravity. Okay? And if you're very, very nice, I will tell you why this is my favorite equation of all time. So you can ask me right now, why is this my favorite equation of all time? I'll tell you after the video. That is all.